Hello, hello. Okay. Yeah. Stop sharing. Okay. Can y'all hear me? Okay. So yeah, this week we're gonna be covering convolutional neural networks, right? So CNNs. And we covered some of that last time. We're kind of gonna be going further, talking about more general like architectures as well. Okay, so before we get started, just some announcements. Quiz two is due tonight, and that explores concepts from last week's lecture. Additionally, we have quiz three being released today, and it's going to cover concepts from today and Wednesday's lectures, so CNNs and advanced CNNs, some of the architectures. And homework one is due Wednesday, right? So remember to submit your predictions on Gradescope. If you have any questions, just feel free to post on Ed. Great. So does anyone have any questions before we start? Yeah. Do you have any like obviously you have the class and all of that. Yeah. I'd say probably in general, like if you have questions, we have office hours on Wednesdays and Fridays. And additionally, right, so I mean you can show up on Wednesday, the homework's due on Wednesday night, or you can also just post on Ed. You can do like a private public post or a private post, and we'll be sure to get back to you. Yeah. Yeah. Okay, perfect. In that case, we will begin. Um, so yeah, in general, we're just gonna be talking about convolutional layers, stacking them together and building a full CNN, kind of the intuition behind these CNNs, and just general things about like training these CNNs that kind of make them different from some of the things we've seen so far. All right, so kind of some things that we covered last time, right? So this is kind of the base of CNN. We have we take our image, right, and we run it through this filter, right? So we talked about convolutions last time. And so given a certain filter, right? So in this example, we have a 32 by 32 by 3 image. And images are normally going to be, with three channels, right? Specifically, like, if you have a colored image, it's going to have red, green, and blue, right? And we run a filter over that image, right? And we take the dot product of that filter with the image at every single point, and in the end, that results in this activation map, right? And this activation map is kind of also known as a feature map, just because this filter allows us to kind of learn features from the image, right? And so for example, right, we can see that if we had six of these filters, we will get six different activation maps, right? And so one for each of our filters. Um, One thing you kind of notice here is that two things, right? The initial image had three channels, while our new activation map, right, we stack them together, we get it has six layers, right? And so that's one thing to always keep in mind, which is the depth of the layer that you get, right, after performing some amount of convolutions is not necessarily, it doesn't really have to do with the depth of the original layer. Rather, it has to do with how many filters you're using, right? And then as you can see, we went from 32 to 28 by 28. That's because our filter, right, had dimensions of 5 by 5. And so when we run it across, we can only go 28 times before reaching the end of the image. Right, so does anyone have any questions about how this works? Yeah. Yeah, lecture slides should be posted. If they're not posted yet, they will be on the Notion on the website. And so yeah, you'll be able to refer them whenever you want. Okay, so another way to kind of think about this is kind of just the same concept, right? We have, for example, in the example, we see with this picture of a dog, we have this 3 by 3 filter, right? And we kind of just, we do this dot product, then we shift it over, we do another dot product, keep shifting it over, and let's say it had a dimensions of 224 by 224 with, right, three channels. And so we have these four filters, right, like the blue, orange, yellow, and purple. And we take each of those filters and we run them over our image, right? And so for each of those images, we create its own feature map. We stack them together, and our output now has depth four, right? And if you look at, the graphic on the right, the same thing is kind of shown where our filter, right, it has the depth equal to the depth of our original image. And for each filter that we use, we add another layer of depth to our output, right? And so the key thing, right, especially when you're also kind of building your own CNNs, is that our filters, right, the number of channels of our filter has to equal the number of channels in the layer that we're trying to kind of apply this convolution to, right? Yeah, right. So now, right, we talked about, stuff like paddings, stride, right? And so we can kind of generalize, right, the dimensions of our output, right, with this like kind of general formula. If we think about it, our input, it has C channels, and the dimensions are H by W, right? Channels by height by width. And each of our filters, right, is, we run F filters. And so the output is going to have a depth of F, right? So F by H prime and W, right? And the H prime and W prime kind of represent this new height and width that depend on factors like the size of our kernel, right? The size of our filter, the amount of padding we use, right? And the stride that we use, right? And so this formula kind of takes it all into account. We take, for example, the width, right? For this is just one dimension, right? But we take the width minus the size of the filter. Um, and then we also add two times the pad, right? Because the padding is on the left and the right. It's kind of all around the image. And then we divide it by the stride, right? Because the stride, the larger the stride, right, the less kind of outputs we'll have because we're taking larger steps. Um, and so we take, the ceiling of that, add one. That's kind of like a general formula to kind of, help us understand um, how the size of our layers kind of go down. Um, for example, if you look here, we have the original example where we have a 32 by 32 image with three channels, and we applied a filter that had dimensions 5 by 5, right? And the stride that we used was one with no padding, right? And so we see if we plug that into the formula, take 32 minus the size of the kernel, right? And so that's 32 minus 5 plus 2 times the padding, right? There's no padding, so it's just 32 minus 5, just 28, divided by the stride, or 30 minus 5 is 27, my bad. Divided by the stride, which is 1, so 27 and then plus 1, right? So we end up with 28. Um, and in general, this kind of just helps, right, when you're kind of like creating your own layers and you kind of want to figure out what each successive layer should be. Um, and oftentimes as well, it's you can just print out the sizes of your layers. That'll kind of help you debug as well. Right. So does anyone have any questions about like this formula or just in general, like kind of how like we have these various factors that kind of affect um, the size of our layers? Yeah. 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 Depth of layers and number of channels. Yep. Okay. Um, yeah. So now, right, so far we just looked at, take an image, we run these filters, we get a new like matrix, right? But what we can actually do is just stack these over and over again, right? Um, and so what that essentially allows us to do is create these larger and larger networks, right? Where, because the image it's just a 32 by 32, size like matrix, and there's like three channels. Now, when you apply, a bunch of filters, you get essentially the same thing. You get a matrix with some number of filters, right? And so we can just kind of stack these convolutions, on top of each other. And again, right, keep in mind the number of channels in each filter, right? is equal to the number of filters in the previous layer. So, for example, if your layer is 28 by 28 by 6, right, your new layer, then if you apply a filter on that, right, that filter would have to have a depth of 6. So maybe you'd apply like 3 by 3 by 6 filter, or like a 5 by 5 by 6 filter, right? Okay. Then we also have this concept of a receptive field, right? And essentially what it means is, we have a bunch of cells, we perform a convolution, and we end up with a new matrix that has a bunch of cells. Now, receptive field is for every cell in our new like kind of matrix, um, each of those is affected by some number of other cells, right, in the previous layer. So, for example, we take a 5 by 5 image, and then we apply a 3 by 3 convolution on it. Then we get like a new 3 by 3 uh, layer, and then we apply another 3 by 3 convolution on that. We end up with, one cell. And at the same time, we can also do like just one single 5 by 5 convolution, right? And that still results in all these 5 by 5 cells. You end up with just one cell, right? And essentially, the receptive field of each of those cells at the top is that entire 5 by 5 grid, right? Because essentially, every single cell in that 5 by 5 initial grid is affecting the value, right, of that topmost cell, right? So that's kind of the concept of this receptive field, which is basically, you have this, cell, and you're basically asking like which other cells in the initial like input was affecting the value of that cell, right? And so here's just another example. Suppose we take this image, right? And we take this 5 by 5 area, right? And so first we apply a bunch of 3 by 3 convolutions, right? And that essentially shrinks our area. Now we have a 3 by 3 area, right? Where that one blue cell was calculated using the 9 blue cells in the original image. So we would say that the receptive field of that one blue cell in layer two was the 9 blue cells in layer one.
So, are we running each filter over the original image, or are we running each filter over the last activation layer?
Yeah. So essentially, right, in this example, for example, like layer one is the original image, right? And so we run a filter over layer one to get layer two. And so that's not the original image anymore, right?
Right.
But then we would run another filter on layer two to get layer three. So it's we're running different filters each layer, right? And these filters, you know, have weights, right? And we'll be talking about that as well later. Yeah, so from layer two to layer three, now that 3 by 3 area turns into this 1 by 1 area, right? And so we would say that the receptive field of that one yellow cell in layer three was essentially the whole 5 by 5 area in our layer one, right? In our original image. Um, and so that basically allows us, right? Like for example, here's like a very high level example. If there's a car, right? There's a car in that orange area, it might be the case that after running it through those layers, that one yellow cell might say, does this cell have a card, right? Um, and so by using this like concept of receptive fields, we're able to kind of encode information about this large image in less dimensions, right? Um, yeah, right. And obviously this is not like actually how it's gonna work, just because like the layers aren't really that interpretable. Like we can't say, oh, these cells, kind of tell whether there's a car, and these cells tell whether there's a person. But that's kind of just the general concept, right? Is that we take this like larger image and we focus on specific features of that image and kind of encode them as we go from layer to layer, right? So the question is, right? We go back to this example of two successive 3 by 3 convolutions versus a 5 by 5 convolution, right? Um, Basically, we really want to manage the size of the receptor field, because if your receptor field is too small, right? If you're trying to do, you have a picture where the whole picture is taken up by like an animal, and you want to identify the animal. If you have small filters, there's no way that any of those filters will be able to detect like that you have an entire animal in that image, right? But on the other hand, if you have, filters that are way too large, what happens is that you're basically trying to take all like the whole image right? And you're taking all the information at once, which essentially makes this the same as like a fully connected dense neural network. And that's kind of what we're trying to avoid, right, with DNS, is that we're trying to use less parameters while still being able to get these features, right? Um, but now, right, the new wisdom, we kind of like wanted the fact that large receptive fields can still do good. And there are some example, vision transformers, Swin, all these, right? They have large receptive fields. They're still very successful, right? Yeah. So now we kind of get to the question, right? Are two 3x3 convolutions the same as one 5x5 convolution, right? And so does anyone have any ideas why one might be better than the other? Yeah.
The two 3x3 convolutions might, each individually pick out small parts, but not in the efficient way.
Um,
That could be like two wheelbarrows on as good as one bulldozer, you know?
yeah, yeah. I think that kind of goes back to like this old wisdom, right? Where the larger ones, or I guess, see, yeah, I guess like the old wisdom of like small receptive fields, like missing things. Okay. Well, yeah. Yeah, yeah, exactly. Right. The fact that with CNNs, we're trying to reduce the number of parameters, um, instead of passing it to like a fully connected, like dense neural network, right? Where we have parameters for every single cell. Instead, now we have less parameters, right? And by doing two theoretic convolutions, we only take up, 9 plus 9, 18 parameters that we have to learn versus, 5 by 5, that can be 25 parameters. And obviously, there's a small image. When you scale it up, right, you essentially end up with it, you know, very large factors of difference, right? And so through the convolution, right, there's less parameters, and then we also have more nonlinearities, right? This kind of goes back to the whole reason why we include these nonlinearities, right, to help it learn better functions. Um, and so we're able to kind of put this nonlinearity in between, right? Yep. And so, just a little recap of pooling layers, which we talked about last time, is that, pooling layers, they help you reduce output size. You apply them to each channel separately. And essentially, we have max pooling and average pooling. Max pooling takes, as in the name, right? We take the max of, this sort of area. And then with average pooling, we take the average, right? And kind of the reason for this is because, generally in an image, right, neighboring features are probably similar. So, we're able to reduce the dimensionality of our layers while not losing too much information, right? Especially like, for example, average pooling, a really simple example, if you want to take an image and kind of downscale it, right? You take the average of like 4 cells that are next to each other, it probably maintains a similar value to what was there before, right? And so again here, right, max pooling, you get like the strongest features in an image. Average pooling, you can smooth it out. You can essentially, preserve this information, right, while still getting like a smaller size, right, for the layer. Right. And then, there's also normalization, right? And we talked about this during gradient descent. Um, but essentially, right, we have different kinds of like normalization that we do now that we have, these 2D, 3D like matrices, right? And so 1D batch norm, you can normalize each of the elements in a feature vector, right? So just like you think about like a vertical vector, horizontal vector. 2D batch norm normalizes each channel, right? And that's usually like the one that people use most. It normalizes each channel based on, the like batch of features, right? And so it basically learns, rescaling for each channel. And that, usually helps because sometimes different channels are used for different purposes, right? And so by keeping these channels separate, it just kind of helps with that, right? And yeah, just like final thing, right? Normalization. You can really do normalization many different ways. You can do it, um, you can do it over the spatial dimensions. You can do each channel independently, right? You can only do some of the channels, right? But essentially, right, there's a lot of different ways to normalize these, and the whole reason why we do it is just, we want better gradients. We want, gradients to be a reasonable size. So we want to prevent exploding or vanishing features, right? And then, the network, right? It has linearities in it that will enable it to scale up or scale down, right? So you don't have to worry about how normalization will essentially affect the network because of how it's able to kind of scale itself back up, right? And that's something we learn. So let me just okay. So yeah, does anyone have any questions so far? Okay, perfect. So yeah, now let's get into kind of building a CNN, right? So we went over kind of how these layers work, how these individual layers work. Now let's kind of look at putting it together, right? So we talked about how we take an input image, we apply a bunch of convolutional layers, right? We can do pooling, we can add non-linearities, we can still add stuff like ReLU, but in the end, right, we end up with this final like set of convolution layers that really, we end up with this like matrix, right? And so what do we do with it now? Now, right, now that we've gone through all these convolution layers, we probably, learned more about features of the image. Now we're able to flatten this, right? And so we flatten it by just, we basically just turn it into a 1D, right? Set of nodes. And then from there, it's just a fully connected network like we've seen before, right? And we can do whatever we want. And for example, if you had like a classification task, you would use these convolution layers, right? To kind of learn like the features of the image, right? Because, with convolution layers, you're able to have these filters that are able to learn when certain features are present. And in the end, once you extract all that information, you're able to flatten it and then put it through this like classification part at the end, which now given the features, it's able to work very nicely, given that we've also reduced, right, the size of our initial input, right? And so for example, in this case, right, we're taking an image, we're trying to classify what kind of object it is. And so we're able to put a softmax at the end to get these probabilities classified. Right? And so just kind of building blocks, right? We covered convolutional layers, right? Stride, padding, kernel size. Those are all things that we choose when building our network, right? They're hyperparameters. Um, Pooling layers, right? These allow us to shrink the size of our matrices, right? We can shrink the features, but without losing too much information. We have max pooling, average pooling, and then we have these classification layers at the end, which flatten the features. We pass through a multi-layer perceptron, and then they usually have the most parameters, just because you're essentially taking now you have this whole like big 1D uh, vector, and then you're trying to um, make like a fully connected layer for that, right? And that's usually where the bulk of your parameters will be. But at the same time, right, it's better than what we would have started with, which is just, we have this image with this first of all, it's larger, and second of all, we haven't extracted any information from it, right? And so a multi-layer perceptron is going to find it really hard to extract that information, right? So this is an example of LANet. It's one of the first like convolutional neural networks, and essentially it kind of works in the same way. You take our input, right? We perform some convolutions to kind of scale it down, extract some features, right? And then after that, right, after we do that a couple of times, now we have a bunch of smaller feature maps, right? And so that kind of localizes, right, each of the features. Maybe some will talk about whether there's a vertical edge, some will talk about whether there's a horizontal edge, whether it's curving, stuff like that. And then we pass that information now into our fully connected layer, right? And then from there, we have our fully connected layers, we have our activation functions. In the end, we kind of get this output, right? And in this case, because we're identifying like handwritten digits, the output would be like a set of probabilities, right? To determine like kind of what class it is. Um, and so, right, in general, just to kind of generalize this, right? For any like CNN, right? Essentially, this is kind of the structure. We have our input. Um, Many times it'll be like, for example, three channels, red, green, blue. We pass it into this convolutional backbone where we can have structures like, for example, convolutional layer, activation function, and then pooling. We can have convolution, activation, and then pooling. We can add batch norms in there. That part is really kind of trial and error. After we pass it through all these convolutions, right? We get our features, we then flatten it, and then we pass it through, right? We pass it through this classification head, for example, and there is where we have our fully connected layers. We have again more activation functions there. Um, and at the end, right, we have a final activation function, and then we get our output, right? And so does anyone have any questions about this? Yes. Um, I think that usually, like many networks, even after you like, kind of flatten it, right? You usually want to apply at least one fully connected layer just to kind of get it into the desired um desired output shape that you want. Um, but like because I mean there are networks that are like essentially fully convolutional, but even at the end of those, you kind of have these like just at least like one or two like fully connected layers. Um, because at the end of the day, right, this backbone mainly deals with like extracting these features. But for example, sometimes you want to take some of these features in conjunction with each other, right? At the end. So I guess yeah, you wouldn't necessarily take the output of all these convolutions and pass that directly to the output. You usually flatten it and then maybe like at least do like one set of like fully connected layer activation and then you have your output. Okay. That case, right? So I guess yeah, just like general question for you guys, right? So we have our current setup, right? We have our layers. Can we pass in images, right, of any size to a standard CNN with an MLP classification layer?
No, and then go on specific size image.
Yeah, yeah, exactly, right? And so essentially, right, the convolutions themselves don't actually depend on the size of the image, right? Because we're just passing a filter over that. But what happens is after we go to our, after done with all of our convolutions, we flatten it. Now that vector will be a different size depending on the size of our input image, right? And so the size of that flattened vector or depends on the dimensions of the input image. Um, yeah, yeah. So I guess in the real world, right? Um, let's say you had an image that was twice as large, right, as the ones you'd feed into a network. You would probably, right, take that image. You have a couple options. You can simply just do like something like a pooling layer, right? It would just downscale it. Um, or you can just add another convolution layer, right? That because we know that convolution layers, right, those downsize images anyways, we could just add one of those in front, right? But in practice, right, if you're trying to have a model right? And you want to deploy that model, right? To be able to take in any set of like images, you kind of have to, right? There's no like you're essentially right. Your network has been trained to take a certain size image and extract features from that, right? Now, if you give it, for example, a larger image, some of those features might be like blown up. Some of those features might be like, or if you pass in a smaller image, it might be like blown down, right? And so in general, right, we want images to kind of be a certain size. Oftentimes, what you'll do is if you have a data set, right, that contains images of like a certain size that doesn't really match with the input that you want, you can apply transformations, right, to the image, right, to kind of rescale it, to get all of the images in your data set to fit to like the model that you want, right? And so we'll kind of talk about those transformations later as well. That's kind of like the general fix, right, that we do for images, right? And just a kind of tip, this is more of the implementation side. But usually, you kind of write these convolution layers and you get to this part where you have to flatten them, right? And oftentimes, if you don't actually want to calculate the size of that linear layer, you can just, print the shape of the output. There's some libraries that will actually just, you can actually have your like layer, like you can actually have your network as a class and you can test like applying random input to it, right? And it'll tell you like the size of each like image at each layer. Right? So stuff like that is kind of helpful. Yeah. Okay. So kind of intuition, right? Why do we want to extract these kind of representations, right? For example, what we might do, right, is if you can kind of think about at each layer, each of those boxes represents a filter, right? A filter that's trying to learn a specific feature. Um, this is like an example, right? This is potentially what might happen usually, right? We're just, we're using like all these like um essentially deep learning, like the layers aren't really interpretable. But for example, if they were, right, this is what it could look like. For example, the first layer, we would apply some filters, we'd be able to determine like specific features, like maybe like vertical edges, horizontal edges, places that are like entirely one color, stuff like that, right? And we kind of looked into that during the last presentation. We talked about just, hand engineering these features. Then, for example, the next layer, it takes the information from the previous one, right? And it's able to, for example, build up these bigger features, right? Such as maybe like parts of an eye or like parts of a mouth. And then one layer above that, it combines those features together, right? Because we know that these convolutions are done over all the features at a time. And so it's able to use all that information to kind of create, right? To kind of get more information about other certain features, like for example, different faces, right? So that's kind of like a general way that it builds up from having this image with only three types of information, red, green, blue, to having, these smaller size like maps that contain more types of information, like certain features that might be there, right? And so it goes from this like lower level to higher level features. Right. So does anyone have any questions about that? Yeah.
So we have a spotlight of the layer like this, like where like the max volume.
Yeah, so essentially this is kind of like a higher level thing, but essentially you would have like, for example, if you had a convolution, you'd probably have some sort of activation function of after that max pooling, and then you would kind of get your output after that, right? So this is just kind of like a representation of like what each like layer would look like after you do like your activations and your pooling and all.
So like that, max volume would be like between.
Yeah, it would be in between each of those layers. Okay. Right, and it's just this, yeah. So essentially, right, with machine learning, we kind of have this representation of the this network, right? And we say, oh, we're trying to learn these features. But at the end of the day, all of the weights and like all of the variables in our network are essentially learned, right? That's like the whole concept of deep learning, where we essentially treat it like a regression type problem where we have these, variables, we don't know what they are, but we find out what they are, right? And so that's just kind of right, this whole process. And so this is kind of like the part of machine learning where again it's like not really interpretable, right? We can't say this layer is like doing exactly this, like extracting exactly this feature, right? And at the end of the day, neural networks are some sort of like black boxes, right? We think CNNs learn these kinds of features. Sometimes like for example, as you saw before, like you can hand engineer certain features, to get them from images. But at the end of the day, right, it's like most deep learning models do not have like these interpretable features, right? Um, and so essentially, right, just kind of a way to visualize this, you have this like saliency map, right? And so you can visualize the partial derivative of a feature with regard to each pixel, right? So you can see which pixels of the image have a greater impact on certain features. And so that kind of helps you figure out like in some sense, right, what a feature is like looking for, right? So for example, here, right, we have like different layers, right? And so for example, like what you could maybe like try to see is like, is there a better yeah, okay. So I guess like for example here, right? If you were to look like certain layers, you're able to tell what they're looking for. So for example, if you had an image, right? Like for example, edges, right? You're able to see that like the edges it detects, right, are more visible, right? Because that's what it affects more, right? In a way. essentially each layer kind of corresponds to more and more complex features, right? And so this is kind of like what the general like kind of idea is, right? With CNNs and like building it up, right? Layer by layer. Right. And so again, right, if you look at, right, this is basically, they basically took images, ran them through a CNN, and then you effectively see which patches of that image were, because we essentially saw, right, how we can backpropagate gradients, right? And so we kind of continue this backpropagation and we see which parts of the image are affecting the like weights of certain layers more, right? And so we would see, for example, like in layer one, we have these like lower level features, mostly edges, orbits, patches of color. In layer two now, we combine those, right, to get maybe more complex edges, more complex shapes. And in layer three, we're able to kind of start getting these visualizations of objects. And then further from that, right, layer four, you have like more complex the objects, people, and layer five again, right, just keeps getting more and more complex, right, to be able to kind of identify these features, right? And that's kind of like the really cool thing about CNNs is that it kind of goes from like a lower level to higher level in terms of like learning things, right? And so for example, from layer five, you could literally take like one of those cells, right? So for example, at layer five, you flatten that, right? Now each of your cells is essentially saying, right, we have like, does this contain this object or not, right? And we're able to build up from that by taking these pieces of these image and these features and slowly like looking at them together. Yeah.
I don't really know it's organized. Like if you go back to the comment, you went to
Oh,
you search, how do you know, or how does machine learning model know that it's served in like
yeah. So essentially, right, the stirring essentially just refers to, right, our back propagation, right? And we're able to tell it to kind of go in the right direction by, by gradient descent, back propagation, right? We essentially know what it's supposed to be doing, and we kind of nudge it in that direction, right? Um, and so it essentially learns weights in order to be able to give us the outputs we want, right? That's the main thing about just training in general, deep learning, is that this model has the degrees of freedom to output, right? Lots of different things. With our training, we tell it which outputs it should be outputting for given inputs, right? And in a sense, that nudges these weights to kind of be able to produce what we want. Right. So training CNNs, right? This kind of differs. So essentially some common just data sets, right? You'll often see like MNIST. It's a very common basic data set. You have 28 by 28 grayscale images. So actually these images only have one channel, right? Which would be how dark they are, right? Because there's no color. But it's a very good like benchmark data set. It's used a lot. CFAR10, I think that's actually one of the most common ones. It's not too large of a data set, right? 15,000 training images, 10,000 testing. Contains 32 by 32 RGB images, right? So it has three channels. Um, and it also has like 10 categories of items for classification, right? So there's 10 categories and has 60,000 images. It's not a bad play. It's a good like it's a good level amount, and you guys will actually be using that in your next homework where you kind of design your own CNN, right? And so another one, right, a slightly larger one. We have ImageNet. It has 1 million images, but now it has 1,000 labels, right? So it has 100 times more labels with approximately like somewhere between like 10 to 100 times more images, right? The images are also bigger, right? 224 by 224. That's a very like that's used as like a benchmark. If you look at a lot of research papers, ImageNet is used a lot for classification, pre-training, image generation, um, and then for other tasks, right? For example, object detection, right? Seeing whether there's an object in an image and where it is, right? We have segmentation to actually take the image apart and say, okay, this area is like this object, right? Or even captioning, where it's just like, saying what object there is in that area of the image. All that, right? All the information, there's a data set called Common Object Context or COCO And that's kind of used a lot for those kinds of tasks, right? And specifically these kinds of tasks, we'll be covering kind of how they exactly work in future lectures, right? And now we get to image pre-processing and normalization, right? So essentially, right, oftentimes we don't just take any images that we get in our data set and pass those right into our CNN, right? First of all, images, RGB values, right? Those are usually in the range from 0 to 255. It's kind of big. So we usually normalize them from 0 to 1, right? Sometimes we normalize them to have specific means and standard deviations. Um, so that helps with the gradients. We also sometimes upscale images, downscale images, crop them just to get them to the size that we want to input them into our model, right? And so that's also pretty important. What else? Sometimes we'll, let me see here. Data augmentation, right? Essentially what the um essentially, right, the higher dimension your data is, right? So larger images, for example, we need more data, right? And sometimes we can't get enough data, right? So what do we do? What we do is data augmentation, right? And so what we can do, for example, is like flip the image, rotate the image, change the lighting. All of that might not look like extremely different to us as humans, but to a model, that makes the model more robust, right? And it gives it more data to train on, right? It kind of tells it, if you see like a cat, but then you see like a dark cat, right? That's technically like still a cat, right? And so stuff like that, if it wasn't in our data set, our model might not be able to know that. By using data augmentations, we're able to make our model more robust, right? For example, we have this one image on the top left, right? And we're able to change the lighting, we're able to kind of scale it, flip it, zoom in, all of that just helps make our model more robust, right? But at the same time, right, you want to be aware of what augmentations you're actually using. For example, right, this is from MNIST, right, recognizing digits. A 9 and a 6 look very similar when they're flipped, right? And so you have to be careful that at the same time, augmenting your data doesn't make some of your data inaccurate, right? Yeah. And so like for example, also like if you have images where you're trying to figure out the location of objects, right? If you flip an image, you have to accordingly update, right? Like the labels, right? The outputs that you want it to give you. And so that's one thing to keep in mind, right? When you're augmenting your data. Additionally, right, you guys will also see this when you're kind of doing your homework assignment. Training CNNs or just neural networks in general, they require lots of compute, lots of time. And so you don't want to lose your work. And so what you can do is you can periodically save the weights of your model, right? And so what that allows you to do is just, you can save those weights, and then if you ever like need to, train the model again or just use the model to do evaluations, you can kind of create like a model that has like random parameters and then put your parameters that you already trained right into that model. And TensorFlow, PyTorch, right? They provide commands that you can use to kind of save your model. And then finally, right, transfer learning. I think this will also show up on your homework. But essentially, what this does is you have networks that have already been trained for very long amounts of time, right? They're already very good at what they do. So why not use that to help you in some of your tasks, right? So for example, if you're trying to make your own model, right, to classify whether an object is like a car or a truck, right? What you can do is use pre-trained layers. For example, ImageNet. ImageNet, there are lots of models out there that have been pre-trained on ImageNet because ImageNet, right, is the data set that has like a bunch of like images with a bunch of categories. You can use layers from a network that's been trained on that in addition to some new layers, right? And so we have covered like frozen layers before, and this is kind of that concept where we take old layers, we keep them, and then we just add some new layers to help it do better for our specific task, right? And so does this make sense? Okay, perfect. So for example, right, this is again another example. We have pre-trained layers, and we kind of, when we're doing transfer learning, we lock those layers that are already good at what they do, right? for example, the convolutional layers, right? They're for feature extraction, right? So why not just keep those as they are because we know that they're good at extracting features. Instead, we just change the dense layers, help us classify for our specific task, right? And so that's like a really useful concept that appears a lot, right, in machine learning, where you take models that are already really good, you add some layers of your own to help it do better for your specific tasks. Okay, now we have lecture attendance. So yeah, that's basically it for today's lecture. We still have 5 more minutes. If you have any questions, feel free to ask. Or else, if you want to leave, yeah, you can leave.
What's the exception?
Today's lecture number. Let me check that. Get back to you. Um, This should be lecture 6. Leave.